Alright, class, we'll continue with trigonometry here on the next unit, which has to do with identities, okay, trigonometric identities. So here we'll be doing solving equations as well as doing what we call proofs, which is probably something you haven't done in any of your previous math courses. Okay, so we'll get to that as well. So first off, here's on this first page, you see some of the identities. Some of these you've already seen, like we're familiar with the reciprocal identities. Okay, and then you see some quotient identities and some Pythagorean identities. And what identities basically are equations that are true for all permissible values. Okay, if variables of the expression are on both sides of the equation. So one of the things you see here is this permissible values. We've looked at non-permissible values already, looking at other types of functions, and we'll begin by looking at these here as well. So let's look at the first example. Okay, so what this question is asking is to list a non-permissible value, and you notice here it specifies to use degrees. You could get the same type of question using radians. Okay, so this is kind of like what we did before when we had different types of equations, and so the same thing is true here. Basically, if something is non-permissible, there's two ways that presents itself. One is that it is invalid. So remember tan theta, how it had those asymptotes, right? So everywhere there's an asymptote, that's where tan theta is invalid. Okay, and the second way you have non-permissible values is whatever causes the bottom of a fraction to become zero. So let's look at the left side here. So we got cotangent x. And so using the reciprocal identity on the previous page there, this is equal to 1 over tan x. Okay, so looking at tan x, again, this is a special one because it has the asymptotes, whereas cosine and sine are completely continuous, so you don't have to worry about that. So here, tan x is not defined. For x equals 90 to 270 and so on. Okay, so again, this has to do, where am I getting this from? This has to do with the asymptotes. Okay, so if you go on Desmos right now and you graph y equals tan x, you'll see the vertical asymptotes, and they occur at 90, 270, and so on. Okay, so it's not defined. So those can't be, or those would be examples of non-permissible values. Now let's continue. As well, because tangent is on the bottom there, we have to look at when does it become 0. So it equals 0. So again, you could graph this on Desmos, and what you're looking for is where it touches the x-axis. And so what happens here is this is for x equals 0, 180, 360, and so on. Okay, and so now let's look at this. So this was looking at everything on the left side of the equation. Let's look at the cosine x over sine x. So sine x cannot be 0, right? And so sine x equals 0 for x equals 0, 180, 360, and so on. Okay, so we've got the value where tangent is invalid, okay, undefined. We've got where tangent is equal to 0 because cotangent is 1 over tangent. And then we got sine, the values where sine is equal to 0 because it's cosine over sine. Okay, so now what you do is you basically combine all these. Okay, so you take the non-permissible values from all the three situations, you combine, and what you have here is non-permissible values are going to exist for 0, 90, 180, 270, and so on. And so what you can do then is give um, an answer that describes all non-permissible values. And so in this case here, your non-permissible values are going to be multiples of 90, right? Where n equals 0, 1, 2, and it would include negatives as well. Okay, so this would be your answer for all values. Okay, so again, when you're looking at non-permissible values, you try to find non-permissible values for all the different trigonometric ratios you can, and then you combine them all into one general expression. Okay, another question is to verify that the left side equals the right side, or through a specific solution. Okay, and so this is kind of what you do when you're checking your answer after you solve for something. You show that the left side equals the right side. So let's start with 45 degrees. So the left side here is going to be cotangent 45, which is equal to 1 over tangent 45. And so you can just work that out in your calculator, and that's going to equal 1. Okay, now do the right side. Okay, so this is cosine 45 over sine 45. Okay, and then work that out in your calculator, and that's going to equal 1. Okay, so this is what we want to show, right? Left side equals the right side. Okay, let's try the next one here. Pi over 6. So again, make sure that you switch your mode to radian mode. Okay, otherwise the answers aren't going to work out. So same thing here. You'd go 1 over tan pi over 6. And that's going to equal 0.577. Oh, sorry, not 0.577. That's going to equal, that's 1 over 0.577. And then you look at the right side, and so here you've got cosine pi over 6, and then sine pi over 6. Okay, so when you're doing this in the calculator, you just basically press the pi button, divide it by 6, and then you can punch in the cosine function. So that would be equal to 0.866. And then you do the same for sine, and that's going to equal 0.5. And then you basically divide that, and that's going to equal 1.73. So here they're not going to be equal. Okay, so the left side doesn't equal the right side. Okay, so again, it's basically the same thing as you would do if you were checking your answers when you solve for some type of an equation. Okay, so let's continue here. Let's look at this next one here. So same idea. Let's try to find the non-permissible values. Okay, so secant x on the top there is equal to 1 over cosine x. Okay, so cosine cannot be 0, and cosine x equals 0. And so this question here we're going to do in radians. Okay, so it can't be equal to 0 for pi equals 2, pi over 2, 3 pi over 2, and so on. Again, you can graph this on Desmos and you can find where it crosses if you're not sure. Okay, and then tan x at the bottom there. So again, it's 0 for 0, pi, 2 pi, 3 pi, so on, and it's invalid so again, these are your vertical asymptotes for pi over 2, 3 pi over 2, and so on. Okay, so again, just combine all these different non-permissible values into one general expression. Okay, so the pattern we have here is 0, pi over 2, pi, 3 pi over 2, and so on. And so you can write this as pi over 2 times n. Okay, and there's your general solution. Okay, now let's get into kind of using those identities on the first page here. So here what we want to do is we want to simplify. So when you're asked to simplify, what you're basically trying to do is to make that whatever expression you're starting with into a smaller expression, and typically what you're looking at here is trying to turn that expression either into a number or a fraction, or trying to get it into a single trigonometric ratio. Okay, so it's either of those that you're trying to accomplish. So what you got to do here is you have to use the identities. Okay, so you don't need to memorize those, just those are written down, right? So just use those identities. And so what we've got here is we've got secant x over tan x. Okay, and so what we know is that secant x is equal to 1 over cosine x. Okay, so now what you do is you take that and you substitute it in for secant x. Okay, so that's going to give you 1 over cosine x and tan x. Okay, and then we can get use another identity, and that is tan x is equal to sine x from cosine over cosine x. Okay, so again, if you're wondering where am I getting these from, I'm getting these from the identities. Okay, on that first page. So now what you do is you take this one and you substitute that in for tan x. Okay, so that's going to give you 1 over cosine x and sine x over cosine x. Okay, so you see what happens here. The cosine x's cancel out, and you're left with 1 over sine x, and 1 over sine x is equal to cosecant x. Okay, and that's your final answer. Okay, so what we've done is we've taken that initial expression and we've simplified it to this single trigonometric ratio. Now, when you do these types of questions, I don't want to see the answer. I want to see how you got to the answer. Okay, so you have to kind of follow the algebra while using the identities to get to the answer here. Okay, and oftentimes when we get to what we call proofs, which are kind of doing sort of the same thing that we just did here, there tends to be more than one way to get to the final answer. Okay, so there's there's more than one approach. Okay, let's look at another one here. So verify that this is, I think, one of the Pythagorean identities. So it's saying verify that is true by inserting 3 pi over 4 into x. Okay, so same as before. It's your left side, right side idea here. So left side, we've got 1 plus tan squared 3 pi over 4. Okay, now if you're wondering how do you do the tan squared, so all you want to do here is take tan of 3 pi over 4, and then whatever you get there, square that. Okay, so that's going to give you -1 times -1, which gives you 1. Okay, and that's going to give you 2 altogether. Okay, now do the same thing for the right side. Okay, so secant squared 3 pi over 4. Okay, and that's going to be equal to 1 over cosine squared 3 pi over 4. And so again, take cosine of 3 pi over 4, and then whatever you get there, square it. And so that'll work out to 0.5, and then 1 over 0.5 is going to give you 2. Okay, and so again, left side equals right side, so that works out. Okay, that's how you verify. Okay, and last one here. Express the Pythagorean identity as the equivalent identity. So there's a couple ways you can do this. We basically want to show that those two expressions are equivalent. Okay, and so what you can do is you can either show that the cosine squared plus sine squared x equals 1, and change that into the expression on the right, or you can take the expression on the right and change it to the expression on the left. Okay, so like I said, there's more than one way to do this. Okay, so for this one, what I'll do is I'll take the expression on the right. I'll take the 1 plus tan squared x equals secant squared x, and what I want to show is that this is identical to the expression on the left. Okay, and so what we want to do here is we want to convert the expression on the right to the expression on the left. So make it become the expression on the left. And so by using your identities and showing that, you've proved that they are equivalent. Okay, so again, there's two ways to go about this. So what I'll do first is I'll get rid of that tan squared x, and I'll make that sine squared x over cosine squared x. Okay, so what I've done there is tan is equal to sine over cos, and so the reason why it's squared is because tan is squared. So it's like sine over cos. Okay. Now what I'm going to do is I'm going to add sine squared x over cosine squared x to 1. Okay, and so in order to add to 1, I've got to change 1 to cosine squared x over cosine squared x. Okay, and the reason why I'm doing that is because I want a common denominator. Okay, so this is just the what the 1 becomes. Okay, and then that secant squared x on the right there, I can change that to 1 over cosine squared x. Okay, so now what I can do is I can add these. So I got cosine squared x plus sine squared x over cosine squared x, which is equal to 1 over cosine squared x. And so you can kind of see what's going on here. Now what will happen is the cosine squared x on the bottom is going to cancel with the cosine squared x on the bottom on the right hand side. And so what you have here is you've changed that now to cosine squared x plus sine squared x equal to 1, which is what we wanted to do. So again, we took the expression on the right and we've made it equivalent to the expression on the left. We made it, essentially we have made it to the expression on the left. Okay, and so that's kind of what we're talking about when we look at what we call a proof. Okay, so again, like I said before, there's more than one way to go about doing this, but it's essential that however you are doing this, you are showing your steps. Okay, so you're not just writing out that they're equal and without showing any steps. Okay, so the steps are really critical here. Okay, so I'll stop there and you can do the corresponding questions.